Hello everyone. Today we will talk about recursion, recursive function, how to write a recursive function, working of recursive function, and Tower of Hanoi problem. Let us start with what is a recursion. Recursion is an important tool to describe a procedure or function having several repetitions of the same. Recursion follows a divide and conquer technique to solve problems. A function is called a recursive function when it calls itself directly or indirectly. Let us take an example. Suppose we want to determine a factorial of a given number. We can express the factorial of a given number in two ways. In first way, factorial of n is equal to n multiplied by n minus 1 multiplied by n minus 2, 2 multiplied by n minus 3, 2 multiplied by 3 multiplied by 2 and multiplied by 1. In second way, we can express the factorial of n as factorial of n is equal to n into factorial n minus 1. The second expression is a recursive description of a factorial of a given number. And first is a repetitive, iterative description of a factorial. Okay. So each recursive function has two major components, a base component and second is a recursive component. Okay. Let us see what is a base component. In base component, we write the problem which is simple enough to be directly solved without making further calls to the same function. Let us take an example of calculating a factorial of a given number. The factorial of 1 is 1. Here we can directly solve this problem. Factorial of 1 is 1. Okay, and this is a base case. Okay, in nutshell we can say in base component we write a base case. Okay, next is a recursive component. Here we write three main steps. In first step, a given problem is divided into simpler sub-problems. In step 2, function calls itself with sub-problems. In step 3, result is obtained by combining the solutions of simpler sub-problems. Let us take again the calculation of a factorial of a given number. Here you can see factorial of n. The problem is determining the factorial of a given number n. So here we are dividing of obtaining the value of factorial of n into two parts, n and factorial n minus 1. Okay, and this is a recursive case of a factorial n. So in first step we divide the problem into sub-problems. Here factorial n is divided into two sub-problems. First sub-problem is n and another sub-problem is factorial n minus 1. In step 2, we write a function which calls itself with sub-problems, and here sub-problems are n and factorial n minus 1. Okay, for factorial n minus 1, the function calls itself with the subproblems n minus 1. Okay. Next, as I have told you, recursion follows divide and conquer technique. Let us see what is a divide and conquer technique. Broadly, we can divide this technique into three steps. First step, divide. Second step, conquer. And third step is combine. So let us see one by one these steps. In divide step, we break the given problem into sub-problems of the same type. Let us take an example. Suppose we want to determine nth term of a Fibonacci number. And the nth term of a Fibonacci number, fib n, is defined as follows. If n is 0, the value is 0. If n is 1, the value is 1. Otherwise, fib n is fib n minus 1 plus fib n minus 2. So here the problem is to determine the Fibonacci of n. And here we divide the determining process of Fibonacci n into two sub-problems. First sub-problem is determining or calculating the value of fib n minus 1. And second sub-problem, calculating the fib n minus 2. Okay, so in step 1, we break the given problem into sub-problems of the same type. So fib n is equal to fib n minus 1 plus fib n minus 2. Okay. Now, in second step, we recursively solve these sub-problems. What are the sub-problems? Fib n minus 1 and fib n minus 2. Here we determine the value of fib n minus 1 and fib n minus 2 in a recursive ways. Okay. Next is the combine. Here we appropriately combine the answers of the sub-problems. What are the sub-problems? Fib n minus 1. And second sub-problem is fib n minus 2. Here, the result of fib n is obtained by adding the result of fib n minus 1 and fib n minus 2. Okay. Now, next is here you can see on the screen, these are the some algorithms that follows divide and conquer technique. Binary search is based on the divide and conquer technique. Quick sort, merge sort, closest pair of points, finding maximum and minimum of a given list of numbers. Okay. Next topic, how to write a recursive function. Let us take the case. Calculating the factorial of a given integer number. And factorial of n is defined in terms of n into factorial n minus 1. And we also know factorial of 1 is 1. Okay. Now, first we write the base component, means the base case. And what is the base case in this problem? Base case is factorial 1 is equal to 1. Okay. If n is 1, then the value of factorial is 1. So here we simply write the condition. If n is equal to 1, return 1. Here the name of the function is fact, and return type of this function is int. And this function takes a parameter n. Now, first we write a base case. And what is the base case? Factorial of 1 is 1. Means If n is equal to 1, return 1. Otherwise, if n is not equal to 1, we write return n into fact n minus 1. So this way, we write a recursive function of a problem which is expressed in a recursive term. Is it clear? Now, let us see working of a recursive function. Okay, suppose we want to calculate the factorial of number 4. So we call the function factorial fact with value 4. Fact 4. Here in recursive function, you can see the first case, if n is 1, then the function returns the value 1. Otherwise, the problem or function is divided into two parts, n into fact n minus 1. Is 4 is equal to 1? No. Now we divide this problem into two parts, n into fact n minus 1, that is 4 into fact 4 minus 1, that is 3. Now here 4 into is a suspended activity and system calls the function fact 3. Again, is 3 equal to 1? No. Again, fact 3, the problem of determining the factorial of 3 is divided into two parts, 3 into fact 2. Okay, 3 into is again a suspended activity and system calls the function fact 2. Again, 2 is not equal to 1. Therefore, this problem of determining the factorial of 2 is divided into two parts, 2 into fact 1. 2 into is a suspended activity. Again, the system calls the function fact 1. At this time, you can see the value of n is equal to 1. And you can see at this time, the function returns the value 1. Means the calling place, that is a fact 1, receives the value 1. Now, next step, combining the results means 2 multiplied by 1 is equal to 2. Okay, this 2 value is returned to the calling place of the function. And what is the calling place of 2 into fact 1 is fact 2. Okay, fact 2, now fact 2 receives the value 2. 3 into 2 is multiplied and this is equal to 6 is returned to the calling place of fact 2. And what is the calling place of fact 2 function is fact 3. Now fact 3 receives the value 6. 6 is multiplied by 4 and this value is 24. Okay, so 24 is returned to the calling place of fact 3. And what is the calling place of fact 3 is fact 4. Now the function fact 4 receives the value 24 and 24 is a factorial of a integer number 4. Is that clear? Now let us take the another problem which is expressed in a recursive manner. So let us see how we write a recursive function for the problem greatest common divisor. The greatest common divisor of two numbers a and b is expressed as follows. If b divides a, then GCD of a and b is equal to b. Otherwise, GCD is equal to b comma a mod b. In this problem, we assume that a is greater than b. If this is not the case, we interchange the value of a and b. Now, first you identify the terminating condition, base case. What is the base case? Here, base case is if b divides a, then GCD of A and B is equal to B. This is the base case. And what is the recursive case? GCD B comma A mod B. Okay. Now, first we specify the return type of this function, integer. Next is the name of the function, suppose GCD. This function takes two parameters, A and B, and both are the integer type. The base case is if B divides A, then the answer of GCD of A and B is B. And how will we represent in the C language? If A mod B is equal to 0, then return B. Otherwise, return GCD. Now we are going to represent the recursive case. And what is the recursive case? GCD B comma A mod B. Okay. And here the mod function is defined by the percentage sign in the C language. So this way we can write a recursive function for a greatest common divisor. Okay. Let us see the working of the recursive function GCD AB. Let us take two integer number 62 and 8. And here our aim is to determine the greatest common divisor of two integer numbers 62 and 8. Okay. In the function, the terminating case is B divides A. Is B divides A means 8 divides 62. The answer is no. Then the control goes into the recursive component. And in the recursive component, we have written GCD, okay, B comma A mod B, that is 6. So 8 comma 6. The system calls this function GCD 8 comma 6. Okay. Now, when this function calls, again we check is 6 divides 8. The answer is no. The control goes in the recursive part. And again the system calls the function B comma A mod B, that is 6 comma 2. Again system checks, this function calls, the system calls GCD 6 comma 2. Okay. Now again in the recursive function we check is B divides A, means is 2 divides 6. The answer is S. At this time the function GCD returns the value 2. Okay. GCD 62 receives the value 2. Okay. And 2 is returned to the previous calling place. And what is the previous calling place of function GCD 62 is GCD 86. The function GCD 86 receives the value 2. And this value 2 goes to the function GCD 62 comma 8. Means function GCD 62 comma 8 receives the value 2. And this is the answer of greatest common divisor of 62 and 8. Okay. Let us see another problem. Finding exponent of two numbers A power B. The exponent of two numbers A power B is defined as follows. If B is 0, the exponent of A power B is 1. Otherwise, exponent of AB is defined A into exponent of A comma B minus 1. Again, we should specify the return type of function, and here you take the name of the function. Suppose name of the function is exp. This function takes two parameters, one is A and another is B. First we write a base condition. What is the base condition? If B is 0, then function, the value of exponent AB is 1. So if B is equal to 0, return 1. Otherwise, return A into exponent a comma b minus 1. Okay, so this way we can write a recursive function for a given a problem which is expressed in a recursive manner. Let us see working of this function exponent of ab. Now suppose we want to calculate 2 to the power 3. Okay, then we call the function exponent with two parameters 2 and 3. Okay, at this time in function the system first checks is 3 0. The answer is no. Then the system goes into the recursive component. In recursive component, here we write a into exponent a b minus 1. That is 2 into the problem of determining the exponent of 2 3 is divided into two parts. 2 into exponent of 2 comma 2. The system calls the function 2 comma 2. Again, here the function checks is 2 equal 0. The answer is no. Again, the exponent of 2 comma 1 is called by the system. And here you can see 2 into is a suspended activity. Again, is 1 is equal to 0? Answer is no. Again, the exponent 2 1 is divided into two parts. 2 into exponent 2 comma 0. At this place 2 into is a suspended activity and system calls the function exponent 2 comma 0. At this time b is equal to 0, means the recursive function at this time terminates and it gives the returns the value 1. Now the exponent 2 0 receives the value 1. And what are the suspended? What is the suspended activity? 2 into and the value of exponent 2 0. The system determines 2 into 1, that is 2. Okay. Now next is the exponent 2 1 receives the value 2 and suspended activities here is the 2. So 2 into 2 the system determines this value and this is equal to 4. And the value 4 is returned to the previous calling place and previous calling place of the function exponent 2 1 is exponent 2 2. Now the exponent 2 2 receives the value 4. Now the suspended activity at this place 2 into the value of exponent 2 comma 2, that is 2 into 4 is equal to 8. Now this 8 value is returned to the previous calling place and previous calling place is exponent 2 3. Now exponent 2 3 receives the value 8 and this is the answer of exponent 2 comma 3, that is 2 to the power 3 is equal to 8. Okay. Now let us take another problems. How to write a recursive function, and problem is nth term. Suppose we want to calculate the nth term of the Fibonacci series. So Fibonacci of nth term is defined as follows. If n is 0, the value is 0. If n is 1, value is 1. Otherwise, Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. Here again, we should specify the return type of the function, and this time again the return type is integer. Name of the function, recursive function is fib, and this function receives the one value, that is a n. Here you can see there are two terminating conditions. If n is equal to 0, the value of function fib n is 0 and the system returns at this time value 0. Else if n is equal to 0, the system returns the value 1. Otherwise, we divide the calculating of fib n into two sub problems, fib n minus 1 plus fib n minus 2, and solves these sub problems in a recursive manner. So this way we can write a recursive function for a given problem which is expressed in a recursive manner. Let us again see the working of this recursive function fib_n. Suppose we want to determine the fourth term of the Fibonacci series. In that case, we call the function fib with parameter 4. Here you can see in the function 4 is not equal to 0 or not equal to 1. Therefore, this problem is divided into two parts, fib3 plus fib2. Now here can you observe that the problem is divided into two sub-problems, fib3 and fib2. Okay. Now plus fib2, these are the suspended activity, and the system calls the function fib3. Now again here 3 is not equal to 0 or 1. Again calculation of the fib3 is again divided into two sub-problems, fib2 plus fib1. Again plus fib1 is a suspended activity, and system calls the function fib2. Here again n2 is not equal to 0 or 1. Therefore fib2 is again divided into two sub-problems, fib1 plus fib0. Now plus fib0 is a suspended activity. Now the system calls the function fib1. At this time n is equal to 1. In this situation the function returns the value 1. Therefore function fib1 receives the value 1. Okay, next 1 plus. In the next step the system calls try to solve the remaining sub-problems. And what is the remaining sub-problems? Fib0. Now the system calls the function fib0. Here you can see the value of n is equal to 0. System returns the value 0. So fib0 is received value 0. Now these two problems are solved. Now next step, combining the solutions of this problem to get the answer of the fib2. So fib1 plus fib0 means 1 plus 0 is equal to 1, and this value is received by the previous calling place of the function fib2. Now fib2 receives the value 1. Now here what is the suspended activity? Fib1. The system now calls the function fib1, and fib1 returns the function returns the value 1. Now fib2 is 1 and fib1 is 1. So 1 plus 1 is equal to 2, and this 2 is returned to the previous calling place, that is a fib3. Fib3 receives the value 2. Now what is the suspended activity? Fib2, and the combining the solutions of two sub-problems. And we have already seen what is the value of fib2. The system calls the function fib2, and fib2 is again divided into two subparts, fib1 plus fib0. Fib1 returns, this function returns the value, receives the value 1, and fib0 receives the value 0. Therefore fib2 receives the value 1. Okay. Now next step, combining the solutions of two sub-problems, fib3 plus fib2 means 2 plus 1 is equal to 3. This 3 value is returned to the previous calling place, that is a fib4. Now function fib4 receives the value 3. Okay. Now next problem is generating a Fibonacci series. We have seen how to generate the first term of Fibonacci number, 0th term of the Fibonacci number, first number of the Fibonacci series, second number of Fibonacci series, third term of the Fibonacci series. Okay, so here we simply write the calling of the Fibonacci function in a repetitive state. You can take the help of the for loop, or you can take the help of the while loop, or you can take the help of the repeat statements of a C language to generate the Fibonacci series. So here I am taking the for loop for I is equal to 0, I is less than n, I plus plus. Simply here print the Fibonacci terms, print f percentage %d, and here we call the function fib. Okay, so this way we can generate the Fibonacci series. Let us take the types of recursion. There are three types of recursion: direct recursion, indirect recursion, and tail recursion. What is a direct recursion? A function is said to be directly recursive if it explicitly calls itself. Here you can see this is the example of a direct recursion. In direct recursion, there is no suspended activity when function receives the value. Okay, in this function, if n is equal to 0, it returns the value n. Otherwise, it returns a n minus 1. So direct recursion means a function is said to be directly recursive if it explicitly calls itself. Here you can see the function a calls itself explicitly. Let's say the indirect recursion. A function is said to be indirectly recursive if it calls another function, which in turn ultimately calls it. Here you can see in this table, the function a calls the function b, and function b calls the function a. So this is the example of the indirect recursion. Next, tail recursion. A function is said to be tail recursive if no operations are pending to be performed when recursive function returns to its caller. And it is tail recursion is most desirable when we are going to write a recursive function for a given problem. And this is due to amount of information that has to be stored on the system state is independent of the number of the recursive calls. Here you can see this is the example of a non-tail recursive function. Here you can see when the function return n into fact n minus 1. Here you can see the n into is a pending operation. When a function has a pending operation, then it is called a non-tail recursive function. Okay. Now here this is the example of a tail recursive function. Here again this is a calculation of a factorial of a given number. Here the function fact returns the call the function fact1 with two parameters n and 1. In fact1 there are two parameters n and m. If n is equal to 1, then function returns the value m. Otherwise, function returns the value fact1 n minus 1 comma n into m. Here you can see the when function fact1 receives any value, then there is no suspended activity. So this is an example of a tail recursion. And here I have shown is how a recursive function works, and you can, it is very easy to understand how the factorial n is calculated. Okay, so therefore I am going to skip this portion. Okay. Next is the Tower of Hanoi problem. Tower of Hanoi is a mathematical game or a puzzle. It is also called the Tower of Brahma or Lucas Tower. And this is one of the main applications of recursion. In addition to this, this game is associated with a legend of a Hindu, a temple. Okay. This puzzle, this game consists of 3 towers, or you can say rods or poles or pegs, and a number of discs of different sizes. Initially, all discs are placed on one tower, one over the other in ascending order of size. That is, the smaller one sits over the larger one. The number of moves required to solve a Tower of Hanoi problem game is 2 to the power n minus 1, where n is the number of discs. Let us see descriptions of the Tower of Hanoi problems and the rules. Suppose there are 3 towers and these towers are labeled with A, B and C. Suppose on tower A, 3 discs are placed with decreasing size. What is the problem? The objective of this game is to move all discs from tower A to C using tower B as an auxiliary tower. The rules of the puzzle are as follows. What are the rules of this game? First rule is only one disc may be moved at a time among the towers at a time. Next rule, only top disc may be moved. Next is a larger disc cannot be placed on a smaller disc at any time. So this is the description and rules of the Tower of Hanoi game. Let us see. This is the initial setup of the Tower of Hanoi game. Suppose we have 3 discs, red, yellow and green, and all 3 discs are placed on tower A. And what is the problem? The objective is here to move all discs from A to C. And A is the source and C is the destination and B is the auxiliary tower. So here the objective is to move all 3 discs from tower A to tower C, that is the destination, taking B as the auxiliary pole or the intermediate poles, with keeping the rules of the game in our mind. The problem is clear now. How will we move these 3 towers from A to C without breaking the rules of this game? In first step, we move the green disc from tower A to tower C. Here you can see. In next step, we move the yellow disc from A to B. You can see in the picture. In next step, we move the green disc from tower C to tower B. Okay. Now in the next step, we move red disc from tower A to tower C. Okay. Now in the next step, we move the green disc from tower B to tower A. In the next, we move the yellow disc from B to C. In next step, we move the green disc from tower A to tower C. And here we solve the problems. Let us count to move the 3 discs from tower A to tower C. What are the total numbers of moves? Let us count it. Here you can see one movement, 1, 2, 3, 4, 5, 6 and 7. So moves 3 discs from tower A to tower C. The total of moves required are 7. Okay. In same way, we can also find the solution for 2 days. In this case, number of moves will be 3. For 1 disk, number of moves will be 1. Okay. Rather than finding solution for each n, let us go back to and let us observe this whole process of movements of disk from tower A to tower C. Let us back. Observe this scenario. What is our problem? Problem is to move 3 disks from tower A to tower C, taking B as an intermediate tower, keeping the rules of the game in our mind. We cannot never put the larger size disk on the top of the smaller size disk. Here you can observe that we can break the entire movement process into 3 major steps. The problem is moves the 3 disks from A to C. In first portion, what we did, we move 2 disks from A to B, taking C as an intermediate step. Okay. In first part, we divide the problem of moving 3 disks from A to C into 3 parts. In first part, first we move 2 disks from A to B. In the case of n disks, we move n minus 1 disk from A to B and keeping C as an intermediate tower. In next part, we directly solve this problem. You can say this is the terminating condition. We move the top of the disk of tower A to destination tower, that is C, directly. Okay, here you can see. Okay, now next, take disk on the tower B as a source and A as an auxiliary tower and C as the destination. We move n minus 1, that is a 2 disks from B to C and taking A as a intermediate tower. So we can classify this problems of moving the n disks from A to source to destination tower into 3 parts. In first part, first we move n minus 1 disk from source to auxiliary. In the next part, we directly move the top of disk of A, that is a 1 disk from A to C. In next part, we move n minus 1 disk from B to C. Okay. Now, this is the case. On the basis of observation, we can reduce the tower of Hanoi problem for n greater than 1 disk to the following sub-problems. Move the top n minus 1 disk from tower A, the source, to tower B, auxiliary. Move the top disk from tower A, source, to tower C, destination, directly. Move the top n minus 1 disk from tower B, auxiliary, to tower C, destination. Okay. Now, here is the algorithms of the tower of Hanoi problem. If n is equal to 1, here we simply print move top disk from source to destination. Is that clear? And return. If this is not the case, we break down the entire problem into 3 sub-problems. Tower of Hanoi, we break into the problem into 3 subparts and solve these sub-problems in a recursive manner. So in step 2, we call the function, the algorithm tower of Hanoi, n minus 1 source to destination, source to destination, and to auxiliary. So here we move n minus 1 disk from source to auxiliary tower, keeping destination as the intermediate. Okay. Next, we simply solve this problem directly. Move top disk from source to destination. In the next step, Tower of Hanoi problem, n-1 auxiliary to source and taking the destination as the intermediate. Is it clear? No. So this is the algorithm of the Tower of Hanoi problem. Now this is the C program. In the C program, you can take any number of disks. Here n, the variable n takes the number of disks. Now we call the Tower of Hanoi problem with 4 parameters. First is the n is the number of disks. And A, B, C, these all are the characters which indicate the tower. A tower, B tower, and tower C. And the function, the Tower of Hanoi, takes the 4 parameters. First is the n, next is the source, next is the auxiliary, and next is the destination. If n is equal to 1, that is the terminating condition, we simply write a message, print move from tower %C. Here we print the name of the tower to tower %C, source to destination. If this is not the case, we break the entire problem into 3 subparts. In first part, what we did, move n-1 disk from tower source to tower auxiliary. And we call the same function with the parameters n-1. What we did, we moved the source to destination, source to auxiliary. Here you can see that the name of the parameter source, destination, and auxiliary. So here we move the n-1 disk from source to destination. But at this time, what is the destination? Destination is auxiliary and actual destination is used as the intermediate. Is it clear? So here you can see the parameters are source, destination, and auxiliary, not the source, auxiliary, and destination. Is it clear or not? And in next case, we move the top of the disk from source to destination, and here is the auxiliary as the intermediate. Directly we solve this problem. Okay. In next case, we move the n-1 disk from auxiliary to the tower destination. Now here you again see the sequence of the parameter. First is the n-1, next is the auxiliary. Since here the auxiliary tower is used as the source, okay, and source is used as the destination. Okay, is it clear or not? Here you can see the sequence of the parameters are auxiliary, source, and destination. Here source is the auxiliary. Okay, source is the auxiliary. So first parameter is the auxiliary, and next is the source. Is it clear? Here, since source is here used as the auxiliary and destination is fixed, means the tower C. So this way we can write a C program for Tower of Hanoi, and output of this program is a movement of the tower between movement of the disk between the towers A, B, and C. For further readings, you can take these references. Any questions? Thank you very much.